Today we're going to be talking about various Elasticsearch use cases. We're going to start out with the basics, the things that you would expect Elasticsearch to do, and then hopefully we will touch on at least one or more use cases that you probably never thought Elasticsearch could be applied to. I will apologize right now for my lack of PowerPoint skills. Those of you that came for fancy animations and transitions, you might want to bail out now. You're going to be underwhelmed. All right, so we'll start with the basics, and we'll talk a little bit about what Elasticsearch is for those of you that don't know. So Elasticsearch is a search engine that's based on Apache Lucene. Apache Lucene is an indexing technology that's been around. I've known about it since at least the mid to late 90s, so it's quite mature. Most search engines do use Lucene. It's been ported to all kinds of different languages. It's pretty much the gold standard for search indexing. I don't really know of any alternatives. All the products that I'm aware of use Lucene, and there's probably no reason to try to rebuild something that's had that long of a head start. So bottom line, it's built on pretty solid search engine technology. Elasticsearch provides all the window dressing around that indexing technology to give you all kinds of nice services that you would otherwise have to build yourself. It's open source, and it has good commercial tools and support through our friends at Elastic. They've really built some incredible tools for doing visualizations, getting data into Elasticsearch, and they've really done a great job of building a framework around Lucene that is approachable and powerful enough for enterprise use. Everything in Elasticsearch is based on, it's all written in Java, so it all runs on the JVM. You can deploy it on pretty much any operating system. Anywhere that you would reasonably want to run a search engine, you can probably make Elasticsearch work there aside from mobile devices, just because you're not going to have the resources to do it. It's accessible to all kinds of applications through a JSON REST interface. Since most of the UIs out there these days are built around JavaScript, and they're all web-oriented in nature, JSON is the native data structure for JavaScript, so that all works great and pretty much works with any kind of development platform that you might want to use. It may be written in Java, but you're not really going to be exposed to that anywhere unless you're writing plugins. So like I said, it's enterprise-grade product. It's designed for scalability. It's fully distributed, so your data, provided that you have more than one machine, your data gets split up amongst multiple machines so that you can do parallel processing and take advantage of storage attached to multiple machines. And everything scales out very nicely horizontally. It's got built-in sharding and replication, so if you have enough nodes in your cluster, if you lose one, you don't lose any access to any data, and performance pretty much maintains. Since it's distributed, you can do lots of parallel you don't have a choice, but internally it does lots of parallel processing, distributes queries across multiple machines very nicely. So it's very performant, especially if you have the luxury of a very large search cluster, which most of you will end up having if you're doing anything other than simple use as a search engine. This thing is in pretty widespread use, despite the fact that it's really not that old. It's only 3 or 4 years old, but you'd be hard-pressed to visit 5 websites and not have one of them that has a significant feature set that's backed by Elasticsearch. We're talking GitHub, Facebook. Most large enterprise businesses that sell products to consumers, their product search is usually built around either Solr or Elasticsearch, and Elasticsearch is taking most of the market share in that space currently. So I know Home Depot is a huge user of Elasticsearch. GitHub's maybe one of the biggest. They use, just looking at their website, you can pick out tons of features of Elasticsearch that it's pretty obvious that that's what they're using. And they have tons of unstructured text data that needs to be searched. and that gives Elasticsearch a lot of stuff to crush on. Also, CERN is using it to monitor the Hadron Super Collider. I don't really know where they are with testing all that, but that's a pretty big endeavor. We're talking about multiple petabytes of data generated in a year that's all dumped into Elasticsearch, and I assume they want to be able to analyze that in a reasonable time frame. So the near real-time features of Elasticsearch, access to data, are really being pushed to the limit there. And they tested several different products, and Elasticsearch ended up being the one that they went with. So that factors in pretty well in favor of Elasticsearch. So we'll back up a little bit, and we'll talk about what a search engine is. So a search engine, as opposed to a relational database system, it indexes stuff in an inverted index so that you can find documents based on things that are contained in it, and statistics about the documents, and statistics about a particular document relative to all the documents that have been ingested into the corpus. So some of the services that you're going to see in a typical search engine are ranking. You can do that a little bit in a relational system, but it's usually pretty limited and slow. Search engines, that's kind of their bread and butter, is coming back with the most relevant search results, as opposed to pulling back things ordered by alphanumeric order or counts or something like that. So that's a big win for search engines. They provide things like word stemming. So if I index a document that has the word run, I can match that on runs, run, running. All of those are synonymous due to the word stemmer when it goes and indexes all the words in the document. And you get that for free with Elasticsearch. You also get regular expressions. Those are usually pretty slow. It's no different in Elasticsearch. If you have really complicated regular expressions, it's going to slow things down. But in general, I find that it does a better job than most relational systems that implement regular expressions. It does things like fuzzy matching, so you can find things based on that might be misspelled. So it uses various different algorithms that are configurable to do the fuzzy matching, so you can give it a threshold, and you can pick different algorithms like Levenstein versus other available algorithms. It has a sounds like soundex type of matching, so I can look for words that rhyme with frog. It takes care of pagination, sorting. It has facilities for implementing synonyms. So if your problem domain typically has words that are referred to by more than one term, you can make a dictionary of synonyms so that when it indexes the document, it identifies a word that has synonyms. It'll also index the synonyms so you can match on those. So a lot of neat things that are really difficult to implement in relational systems or NoSQL systems, or really anything other than a search engine. That's really, all these things are kind of the search engine problem domain, and Elasticsearch has covered all of those. All right, so there's a few different types of search engines that everybody's probably familiar with, the most prevalent being web search. So I'm sure everyone's used Google probably multiple times today. So I'm not going to go into much detail, but it's usually based on relatively simple term-based queries, usually keyword matches, combinations of keywords, and getting ranked results back. Elasticsearch has all the facilities to provide this kind of simplistic searching. So we'll move on to something a little bit more interesting, which is a catalog style search. And so your catalog might be products or real estate listings. It could be people in a directory, businesses, what have you, stocks, pretty much anything. But the real difference is that the data is usually at least partially structured. It's not just unstructured text data. You usually have some metadata. You know that things are somewhat categorized. They have known attributes like price and manufacturer and country of origin and description and all that stuff. And so there's a lot more sophisticated searching that you can provide. So you, instead of just searching for a keyword, you might be able to find things by faceting on, say, category or tags that are associated with a product, or price or color or any of those things. So that makes your implementation a little bit more interesting. Again, Elasticsearch has all the facilities to deal with pretty much everything that you're going to want to do there. These types of systems are usually kept up to date by an internal system. So whenever you update the source of truth, you're indexing or re-indexing documents into the search engine. And you can take your pick of any online store as an example. GitHub's a good example. Instead of products, they're dealing with code check-ins and people and projects and releases of projects. And then there's enterprise search. There's probably a fair number of you on the call that are interested in this type of thing, where you have a fairly complex search problem where you have heterogeneous data, you have database records, you have intranet pages, records and document management systems that are versioned, you have people and organizations and groups in LDAP directories, you got every email that's been sent in your enterprise. It'd be nice to search all of that all those things, and with a little bit of elbow grease, you can make that kind of thing work with Elasticsearch. The real trick there is not so much in what Elasticsearch provides, but it is in putting together all the tooling and infrastructure to recognize changes in your data across the enterprise and get those updated into Elasticsearch so that people can find them. But other than that, it uses pretty much the same type of search controls as a catalog search. It'll be a mix of term-based searching and filter faceting, just like you would do in a catalog based on metadata. All right, so getting the actual search out of the way. Some of the things that Elasticsearch allows you to do once you get your search working is get a little bit smarter about building your queries. So I'm sure you've all seen, you've all accessed a website that does autocomplete. So you start typing and it makes suggestions. Elasticsearch is really fast at doing that. So you can get popular terms to autocomplete into a search window based on AJAX calls from your user interface, and implement a autocomplete solution pretty easily. It also is really good at aggregating different metadata data points that have been indexed into your data, and it keeps statistics on all that, so it doesn't actually have to scan all your data. It just looks at its statistics and sends back counts of documents that match certain terms. It's really easy to implement fasting, and then filtering, narrowing things down by ranges of price or date or things like that. And then also, while you're building up your query before you actually run it to pull back data, running quick checks to see how many records your search criteria is likely to bring back, or it's usually not an exact number, but it's usually a very close approximation. And then once the query has been run, you can also do filtering and or ranking based on a number of interesting things, like if you have location information on the user, which most applications are doing these days, you're able to rank things in accordance with their distance from the current user's location. That's a big one. Google does that quite a bit. Also by language, if you have documents that are indexed in multiple languages, obviously you want to bring back the ones that are in the user's preferred language as being higher rank over ones that are in languages that they probably don't understand. Also, you can rank things based on things that you know about the user, like things they might be interested in, or other metadata about that you have on hand about their user profile, that might give you an indication that one result is more likely to be of interest to the user than another. And we can look at some of these things with just by going to GitHub. I told you there's a lot of stuff on GitHub that is clearly using Elasticsearch. And if we just look at this one search screen, we can see if I type in E, it gives me the autocomplete. This is coming out of Elasticsearch. We see we've got term highlighting. I search for Elasticsearch, and all the instances of Elasticsearch, regardless of case sensitivity, are highlighted. That's all driven through Elasticsearch. We've got these facets over here that are based on programming language. And so it's doing, Elasticsearch has done an aggregation and saying that based on your search for Elasticsearch, we found 1,473 records that involve Java, and then so on and so forth with all these different programming languages. But these are all coming out of Elasticsearch, and it's all done really quickly. That's a single query to pull back all of these with the counts and the search results. And so you also see we've got this sort by best match. And so, if you've ever built an application that's based on relational technology, the best you're going to get is sort by some field or sort by some value. But with a search engine, you have relevancy. So most of the time you're going to want to sort by relevancy, because that generally has the most meaningful results. And if you look at these things, you can see that they're all ranked by relevancy fairly accurately. So the top one is the actual Elastic project, and it matches the most people who have favorited this thing compared with the other ones, and it also has the most user connections. And if you go down the list, you see that they dwindle down in both categories accordingly. And so that relevancy looks like it's pretty accurate. So I would say in this case, Elasticsearch did a pretty good job. And then we've got the pagination. This stuff is all easy to implement with Elasticsearch. Elasticsearch doesn't provide any of the UI facilities, but it does give you all the data in a nice JSON format that is easily consumable by your UI, which is almost certainly driven by JavaScript. So it can easily consume JSON. All right. So moving on. One thing that Elasticsearch also is, and this, I don't know that this was intentional when they started building the product, but in order to facilitate updates of documents that have already been indexed, they store the original document that was submitted for indexing as in a field called source. So you can use this as a NoSQL document store in the right scenario, and take advantage of the fact that Elasticsearch is all distributed and it has built-in sharding and replication, and it's got a flexible schema. Some people like to say it's schemaless, but that's really not accurate. It will auto-generate a schema, but you still kind of have a schema, and most of the time in production you're going to want to define your own schema, so we'll compromise and say flexible schema. So you kind of get this working documents, NoSQL document store that's distributed and has a lot of the same features that you get with Cassandra or Mongo or any of the other popular NoSQL data stores out there for free. Now, there are some limitations. Mainly, you don't want to use it as your source of record, because this product has not been around all that long, and it doesn't focus on being a document store. It's a search engine first and foremost, and so there are some potential for you to lose data in certain scenarios, either at index time or when data is being optimized. I know a lot of that's improving, and it's really getting better. It's far less of an issue than it was when I first started using Elasticsearch, but I would still not quite trust it for using it as the sole source of truth. Sometimes I use Elasticsearch as a NoSQL data store, but I always make sure that I keep timely backups, and I also always make sure that I can restore any data from an authoritative source, usually source files, or I'll have everything stored in a NoSQL data store that focuses on not losing data. So I can always recover things if I need to, but other than that, it's a very convenient document store. And I have built applications that do use it as a source of truth, but like I said, I wouldn't recommend that for large-scale use where it's going to be a disaster if you lose a record or two. All right, so one thing that's kind of surprising to some people, less so these days because this is kind of morphed into one of the largest uses of Elasticsearch, is its use as an analytics platform. So a few years ago, somebody came up with the suggestion that what are analytics but a search problem anyway? And so these guys implemented a bunch of aggregations that aren't terribly useful for searching data in the traditional sense, but they work amazingly well for analytics. And so there's dozens of aggregation types in Elasticsearch, and they're always adding more with every new release. And they've also built a lot of tooling around the analytics use case in the form of an application called Kibana. And they keep adding these great plugins like Timeline for analyzing time series data, which is probably the biggest analytics use case. And then more recently, a graph exploration product where you can go see the interconnections between data. And there's a lot of use cases for both of those things. Kibana on its own, it provides a convenient way to build dashboards and a lot of really interesting visualizations, plot things on maps. It does all kinds of great stuff that's worth checking out. It's really a great, it's really become a great platform for doing ad hoc exploration on your data. So it's good for digging into your data and asking questions where you don't really know what the exact question is, but you can poke around at it and using these tools form hypotheses and come up with theories that you want to test using code that you might have to write. So it's a really painless way to do that, and it's really great for that. Let's see. So the first thing that they really focused on with regard to analytics was something that was originally called the ELK stack. And so that stands for Elasticsearch, Logstash, and Kibana. They've kind of moved away from that because they added this thing called beats for collecting data from different devices, the network, file system, disks, all that stuff. There's a bunch of different beats. You can write your own beats that plug into the system and send data to Logstash, but I don't think Bleck or Belk had quite the ring that Elk had, so they're calling it Elasticstack. So that's the terminology that you're going to hear from this point forward. So the idea is that you collect events from all these different types of data sources, web servers, network devices, the network traffic, application events, pretty much any kind of event that you might get out of a computer system. And you're going to send it into Elasticsearch through a combination of beats and Logstash, whatever makes sense for the particular type of data. And once it's in Elasticsearch, then you can visualize, you can go find individual events, and you can take advantage of all those aggregations and produce some pretty sophisticated analytics in a really painless way, and do it really rapidly. And then you can provide it as, you can bundle those all together in a dashboard, and you can provide it to different user bases. So that's gotten a lot of traction. There's probably more people doing this with Elasticsearch than anything else at the moment. So I'm not going to bother with a demo because you can probably find 100 different demos if you just Google it. and they will all have real data, and they'll do a better job of demoing it than I would. So the next thing that a lot of people don't know about is event percolation. So I will show you a little bit about this. And so the idea behind event percolation is search in reverse. So in this case, instead of indexing documents and then running queries against it, what we're doing is we're indexing queries, and then we're playing documents against them to see if it matches any of the queries. So you might have a bunch of different queries that are indexed, and you will percolate a document and see which queries it matched, and then you can do something based on the outcome of that. And there's two different mechanisms for doing this in Elasticsearch. One is the older Percolate API, and you get that for free with the open source product. It's more suitable towards real-time matching. So if you have a match that needs to get identified like at the same time or close to the same time that you're indexing data or you acquire an event, this is the way you want to go. The real limitation there is that the search match is done in a single document scope, so you can't take into account the entire corpus of documents that you've indexed in doing your match. It only has that one document to go off of. And it doesn't have any built-in alerting or anything, so you got to build that around it. And then there's the Watcher product that's part of their XPack, which that's part of the license product that Elastic sells. And so if you have a license for XPack, you can use Watcher to set up these scheduled runs. And even so, it's not real time, but you can have it run periodically. What you get out of it is the ability to take into consideration the entire corpus of documents that you've already indexed with this document that you're percolating. And so based on the outcome of that, within Watcher you can set up alerts, and these alerts might send an email or trigger some other event or send SMS, or it's got all kinds of different things that it can do. So which one you choose is going to depend on A, whether you have an XPack license, and B, whether you got to do real time or you can be satisfied with a scheduled batch job. So we're going to look at this a little bit. I've got a simplistic little demo that we're going to walk through. And so at the same time, we're going to take a look at how Elasticsearch indexes documents. So this tool that we're looking at here in my web browser is called Sense, and it's a simple Elasticsearch-friendly REST client that lets me run these HTTP requests. So I'm just running a HTTP GET against aliases, and these aliases show me the different indexes that I have in my Elasticsearch instance. And so you'll see that there's not one called Bookstore. And so when we said that Elasticsearch is schemaless and easy to use, we're going to demonstrate that a little bit. And so I'm going to index these books and into an index that doesn't exist. So when I index this, it's going to actually create an index with default settings and index the document and generate a schema for my document, all without me doing anything. So I ran it, and we got a successful response. So now I have this book in there. And so if I want to retrieve my book, let's see. I can run just a simple query all search that should pull back everything. We see my book, and I mentioned that it indexes the source whenever we index stuff, and so you can see that's exactly the document that I indexed up here. And so let's put a few more records in here so that we have some more interesting data. Let's see, and we'll put an author in there. And if I want to see the mappings that it generated for all those records that I put in there, I run this mapping query, and it'll show me the mapping that it generated. So you'll see that on the author, my birth date and date of death, it identified those correctly as dates. And so those got created as dates. It identified the names as strings. It identified the page count of the book and the year published as numbers. So everything looks good there. There are a few things that I would want to change about this if I was actually building a product against it, but we won't get into that. It's kind of out of scope for this talk. So having those in place, if I want to retrieve, let's see, book 2, which is of mice and men, if I want to retrieve that by ID, 2 is the ID that I assigned when I index the document, I can run this query and you see that it pulls it back. If I don't want to pull back this metadata that Elasticsearch likes to wrap around things, I just want the source, the exact document that I index. I can pass _source and I get back the exact document that I index. So that's kind of the use case, using it as a NoSQL data store. That was pretty painless to set up and really painless to query. So you can see how that might be really nice to build up a prototype, at least, if not for production use. So if I want to do a query and take something into account, these queries can be as simple as this one, or they can get crazy complicated. I'm going to spare you the crazy complicated queries because we don't really have time to get into all that. But if I run a query for John, you'll notice that I indexed Of Mice and Men by John Steinbeck, and I also indexed an author document for John Steinbeck. So you'll see that this query for John brings back both of them. So when I run a query just for John and it's not scoped to a book or an author, it's going to pull back everything that matches on any field. Now I can narrow that down a little bit. If I only want to search books, I can specify that, and I should only get the one result back for the book, and same thing for the author, depending on what I'm looking for. So you can do, it's pretty, helps if you spell things right. So it's pretty easy to implement both a heterogeneous and a homogeneous search. If I want heterogeneous results, every type that matches back, it'll do that. If I just want one type back, it'll do that as well. So if I want to only query on a single field, like the author field on a book, that's easy enough to do, and I can do all kinds of different queries with different fields. So you can do ranges on dates and numbers and all the things that you would expect to do. So you'll also notice one thing in this record up here. So genre is multi-value. Actually, all of these fields in Elasticsearch, every field can support multiple values. In fact, you'll see that on awards. So the first time I indexed a document with the attribute awards, it was a single value. But then I came along, I haven't indexed that document yet. Getting ahead of myself. All right, so we'll get back to that. So searching, if I want to do a match on different fields, since I can't really match on John Steinbeck, I might get incorrect results based on the way that mapping works. It will match on every word. So if I had enough records in here where I had another author named John, I would match if I didn't also have this AND filter in here. So this query is making sure that the author field has both the word John and Steinbeck in it in order to make a match. So we could keep going on that, but it would take forever because there are literally hundreds of different ways that you could construct a query, and they can get pretty elaborate. So I'll leave that for you to explore on your own if you're so inclined. But we will look at the percolation. So now that I've got some records in there, I can index this query into the percolator. And so that guy's in there now. And then I can percolate this document. And this has basically the same structure as these other documents up here, but it doesn't exist in that set. I haven't indexed that document yet. So if I run that against the query that's looking for John Steinbeck, you'll see that it came back with one match. And so ID1 is this, this percolator query. So I know that this document that I submitted matches that. And so percolation is working. If I submit this other lesser-known novel, The Onions of Discontent by Jerry Steinbeck, I don't get any matches because it doesn't have John and Steinbeck in the author field. So that's pretty simplistic and a silly example, but I'm sure you can see how you could use the Percolator API to do some pretty useful stuff, especially with regard to events. If you want to find error messages and all kinds of stuff like that, Percolate is a pretty good way to identify those at ingest time. You can also percolate an existing document. So I've got this Percolator job that is looking for John Steinbeck, and I have document 2 is of mice and men, which we know is by John Steinbeck. So if we run this, you'll see that it also matches the query, and all I did was provide the ID and underscore percolate, and we're good to go. All right, so we will get back to our slide deck over here. I think we've covered event percolation. All right, so another thing that's kind of emerging for Elasticsearch is statistical anomaly detection. So anomaly or outlier detection is the identification of items, events, or observations which they don't conform to an expected pattern of established historical data. So if you have enough data, it's easy enough to build a system around Elasticsearch that can do anomaly detection. Anomalies might translate into something that's important and require immediate attention, like fraudulent transactions, medical emergencies, some kind of structural failure in a building or aircraft or whatever, breakdown in some manufacturing process. As serious as those things are, oftentimes they escape timely detection due to the volume of data that the telltale signs are hiding in, and the difficulty in ferreting out those signals and identifying that there's a problem. So anything that can help identify those anomalous signals more accurately is a huge win. So there's some really smart gentlemen at eBay that came up with a relatively simple but effective anomaly detection algorithm that they're calling Atlas. And they were kind enough to share it with the tech community at large. And some equally smart folks at Elastic took that algorithm and came up with a pretty good implementation using Elasticsearch and a plugin to Kibana called Timeline and their Watcher product. And so there's a 3-page write-up of, or a 3-part write-up on the Elastic site that details how to implement that for yourself. Probably everyone is interested in anomaly detection, but it is way too in-depth to cover in this talk. It's at least one talk on its own. So if you're interested, just Google anomaly detection with Elasticsearch, and I'm sure you'll find that pretty quickly. It's worth a go through. It goes through all the theory and how to implement an Elasticsearch. I highly recommend it. Another thing that's really popular these days is recommendation systems. Recommendation systems, they gather relationships between people and things in order to make recommendations about information that the current user might be interested in based on what other people with similar interests are linked to. Utility recommendation system, it's penetrated everywhere. You find it for books, movies, music, news, products of all kinds, search queries, social connections, dating profile recommendations, pretty much everything. Oh, and let's not forget advertising. They were probably the first ones of it. So there's several different ways to do recommendations in Elasticsearch. The first one that we're going to look at is something called the significant terms aggregation. This is what some people refer to as the uncommonly common aggregation. And so the significant terms aggregation, it factors out the base probability of a term and suggests terms that are both relevant and uncommon. With just this one aggregation, you get a dead simple yet fairly decent option for making recommendations right on the box. So let's switch over and take a look at that. And so I need to switch over. So for some reason, I had to pull up my data set in a older version of Elasticsearch. So that version isn't working with Sense because it's a little bit too old. So we have to go back to my garden variety REST client, good old Postman. So we'll poke around at our data set a little bit here first. And if we look at our data set in Elasticsearch, this data set has a bunch of movies, and it has users that have indicated that they like those movies. So two different types of records in here. Now we're going to do a search for Talladega Nights, and so if we do Talladega Nights, we hit on the right movie as our first result. So we're going to take this ID for the movie, and we're going to refer to the movie preferences, and I've constructed a query here that takes the ID for Talladega Nights, and it uses the terms aggregation that's going to find the most popular terms for 6 movies in the movie field that are similar to this guy. So if I run this, we're going to get back these 6 records, and then we have to go resolve them against the other table. And you'll see that we come back with some mixed results. So we get Pulp Fiction, The Matrix, Fight Club, Star Wars Episode 4, and The Shawshank Redemption. Those are not great matches to Talladega Nights. I don't really see any correlation. And so the problem there is that these are popular movies that most of the population likes. So they're kind of false positives because of their overall popularity. So the significant terms aggregation is going to help us filter those things out. And we can confirm that those are popular movies just by running a query against everything and look for the most popular movies. And we're going to come back with a list that at least 50% matches the list that we got when we ran with Talladega Nights. So yeah, there's Pulp Fiction, Fight Club, Star Wars Episode 4, and Shawshank Redemption. 4 out of our 5 results are a match, whether we search for Talladega Nights or not. So that's obviously not going to work. Where the significant terms query comes in, we're just all I've done is run the same query. Instead of terms here, we run significant terms. It's going to filter out the noise. So if I run this guy, we get back our results. If I correlate those back to the movies table, we're going to see that we get Anchorman, 40-Year-Old Virgin, Semi-Pro, Blades of Glory, and Knocked Up. And if you've seen any of those movies, you know that these are all much more similar to Talladega Nights than the original list. So based on this, I'd say that it's working pretty well. These all look like pretty reasonable matches. If I've said that I liked Talladega Nights and I get matches, at least 2 or 3 of these have the exact same actor in them. So I would say that that's working pretty well. So that's your significant terms. That's useful for all kinds of things. And it's super easy to implement. So that's a win right out of the box. So there's also a more like this API. And I don't recall if I have a demo. But basically the idea is that you find a document, and then you run it against the more like this API, and it finds the documents that are most similar to that. Let's see here. Yeah, unfortunately, I don't think I got around to making an example for that. Sorry, but it works. It works kind of like the Percolate API. You provide a document, and it'll find documents that are similar. You're not looking for exact matches. They're just recommendations. It's another mechanism that also provides you with some valuable results, and it's worth checking out. All right, and then we've got something that's relatively new, which is the Graph Explorer API. And so this is both an API as well as a UI plugin for Kibana that you can use to visualize the results out of the Graph API. And I do have a demo for that. We'll look at that right now. So let's see. This is the Graph search product. And so if I do a, actually I already had previous search results here. Let's get rid of that. So if I do a search for Metallica and I'm looking in radio user preferences data, if I do a search for Metallica, I'll see a bunch of bands that you can tell are related. Judas Priest, Megadeth, all those guys. And if I want to expand that, I can pick up a few more, but it's clear that these are all related. And I can look and see, I can click on each one of these connecting lines and I can see what the overlap is. So the overlap is their shared connections to other things. And I can poke through that. There's all kinds of other features that you can use in this graph interface. I'm not going to attempt to fool with them because I'm not an expert with this, and it's relatively new. I haven't had a chance to play with it too much. But it's pretty clear that it does it, and it's good for, it does what it's intended to, and it's pretty good for exploring different relationships in your data. You can expand any of these things out as much as you want to. And you can usually find some pretty interesting connections that you probably want to investigate further with more pointed queries. Let's see. So switching over to the API side, so this is more my domain. I can do the same kind of thing with the Graph Explorer API that backs that user interface if I was doing this programmatically. So if I put in Metallica, I'm going to come back with pretty much the same results that you saw in the UI. Just I get them back in a JSON format that's a little bit easier to work with for application that I'm writing. So I can take advantage of this graph exploration within an application. And then if none of those options cut it, there's an integration that's available for connecting up to a machine learning framework called Mahout. And so once you implement that, the learning curve is going to go up, but you're pretty much boundless on what you can do as far as elaborate schemes for making recommendations. So you can knock yourself out there. We're not going to get into that because that's a whole talk or two on its own. All right, and something that I've seen recently that is interesting is doing image similarity searches. So this involves doing a little bit of pre-processing on image data or media data and fingerprinting it and extracting and tagging the image data so that you can do searches on it. So you can find exact matches or things that are similar to an image. And there's several different ways to do it. So there's this Lyra plugin, and it's really a Lucene plugin that allows you to do content-based retrieval on image data. And what you do is you pass in an image as your search criteria, the actual binary image data, and it goes out and finds images that are similar to that. And it does a good job of matching based on overall color scheme and color balance. It doesn't do such a great job on picking out people or birds or koala bears or any of that. But it does come up with things that match from a color perspective. So I wouldn't recommend trying to use this as a standalone, but if you combine it with a few other things, this image similarity and categorization can work quite well. So the first thing is this perceptual hash, p-hash. That's something that you're going to want to run on an image before you submit it to Elasticsearch, and it kind of fingerprints your media file. And it does do a much better job. It kind of does the opposite of the Lyra, and it picks out shapes and things in an image and fingerprints those so you can do matches against that. And the hash that it produces does a fair job of pulling back images that roughly match the same types of shapes and content within the image, ignoring a lot of the color data. In fact, if you submit an image in color and the same image in black and white, the matches that I've seen came back as exact matches. So it works great for shapes, not so great for colors, and Lyra does the opposite. If you combine those two together, you got a pretty decent solution. If you want to take it farther, there's a machine learning framework called Deep Detect that works on images, and it does a good job of tagging. You kind of have to do some training on it, just like all machine learning frameworks, but if you put in the work, you can have it identify specific things that are in your image, birds, people, cars, specific models of cars, all kinds of things. Depends on how well you want to train the thing, but it can tag the items that it finds in your image data, and it can provide those back as metadata, and then you index those with your image, and then you can do filtering, faceting of your image records based on the tags that it extracts out of your image based on machine learning. So that's all pretty cool stuff. There's a lot of applications for that as well. It's not quite so common as the other things, but it is interesting if you have a use case for it.